We start with Kostenecki acylation reaction. I hope you might have seen this reaction in your previous semesters. So it is an acylation reaction of orthohydroxyaryl ketones with anhydrates, usually acetic anhydrate, followed by cyclization to form chromones or coumarins. And we know chromones and coumarins are basically isomers and they are derivatives of benzopyran. And in that benzopyran, a substituted keto group will appear. Substituted keto group will appear. So, Kostenecki acylation or reaction is basically a cyclization reaction or a cyclic product is formed by the reaction of orthohydroxyaryl ketones with aliphatic acid anhydrates. And we know basically chromones and coumarins are isomers. See here, this is a orthohydroxyaryl ketone. Hydroxy, ortho position, we have the aryl ketones. So OH is present at the ortho position of the ketonic group attached to the benzene ring. So we could say this is orthohydroxyaryl ketone, which is reacting with an anhydrate, aliphatic acid anhydrate, resulting the formation of, see, a chromone. We are getting a chromone or its isomer coumarins. This particular reaction is called Kostenecki acylation reaction. See here, this is coumarin and this is chromone. Coumarin and chromones are only difference in their position of C double bond O. In coumarin, it is the first position, alpha position. So here it is in the opposite position. So basically these two are derivatives of benzopyran, but the presence of ketonic group is at different positions. So during Kostenecki acylation, we may either end up derivative of a chromone or a coumarin. That is why we say Kostenecki acylation will give rise to chromones or coumarins depending upon the condition and the substrate, that is the orthohydroxyaryl ketone that we are using. Okay, take down. Please don't take this screenshot. For BSc it may be okay. So you take down the mechanisms as and when it is explained. Now moving to the mechanism, we could say the mechanism occurs in 3 steps. The first step is the formation of a tetrahedral intermediate by the acylation at the phenolic oxygen atom. So we are using an acetic anhydrate or an aliphatic acid anhydrate. It undergoes reaction at the oxygen of the phenolic group, because we are taking orthohydroxy ketone, aryl ketone. So the phenolic oxygen air acylation occurs to form a tetrahedral intermediate. So the oxygen atom of the phenolic group establish a oxygen linkage with the acetic anhydride, followed by the elimination of acyl group from anhydride. We know anhydride is having two acyl group, R C double bond O, C double bond R. This is a anhydride. So the oxygen atom of the phenol, see here, write down this one. You take down this one, benzene ring, OH, CH3, C double bond O. Take down this, write down this. Now this lone pair of electron of oxygen, the lone pair of electron present in the phenolic oxygen, attacks, see, the carbon atom of the anhydride having C double bond O. This is a acyl group. So it attacks the acyl carbon atom of the anhydride. This is the acid anhydride. R CH2 COO CO CH2R. So this is a acid anhydride, and the phenolic oxygen atom is attacking the carbonyl carbon atom, or we can say C double bond O, because C double bond O could undergo polarization. See the product. So the oxygen is establishing a link here. So this was O minus. Now it becomes OH. Now see here, this H transfer the electrons to the oxygen. Transfer the electron to the oxygen, so that a C double bond O establishes here. When a C double bond O establishes here, this bond cleavage occurs, so that this particular acyl group will be eliminated out, or it will be transferred out from the acid anhydride. So take down carefully. First, the phenolic oxygen attacks one of the carbonyl carbon of acid anhydride, establish a oxygen carbon linkage here. The O minus or OH bond shift towards here, so that the acyl group is left from the molecule, so that we are getting a oxygen carbon oxygen linkage here. That is, a acyl group is established at the oxygen atom of the phenol. Take down. Now we move to the second step. The second step is the intramolecular aldol condensation to have cyclization. See, first step, an acyl linkage was formed with the phenolic oxygen atom, which then undergo an intramolecular aldol condensation. We know what is aldol condensation. So in the second step, that aldol condensation result in the formation of a cyclic compound. Okay, that means the acyl group which is attached to the orthohydroxy ketone undergoes cyclization. So that intramolecular aldol condensation result in the formation of a cyclic ring. That means the condensation group is present within the ring. So it is a intramolecular aldol condensation. See here. This is the acyl group which is established linkage with oxygen atom. Now see here, we have a alpha carbon atom here, alpha carbon atom here. So this is having a hydrogen atom. So that H plus undergo enolization with the C double bond O, so that it will result in the formation of a enol. See, this is an enol. Just look, a double bond, a OH. So if this is O minus, if here it is O minus, it will say enolate anion. Okay. Now see here, this minus sign moves to the carbon-oxygen bond. As a result, this carbon double bond attack, see, the carbonyl carbon atom of the ketonic group present in the benzene ring or attached to the benzene ring. So here a phenol was connected here. Now we have a ketonic group attached to the benzene ring here. So this enol attack this CO. And we know aldol condensation occurs in the primary step. A enolate anion is generated. That enolate anion attacks the second carbonyl carbon atom or second molecule, the carbonyl carbon atom of second molecule. Here it is intra, same molecule. So this enolate ion attack the carbonyl carbon atom present in the benzene ring. So a ring closure reaction occurs. See here. So we get a ring here. OH, CH3, RH. Here is a H is there. CH2 no, H is there. So a ring has formed here. Listen carefully. Take down. So you first draw this one. Show this is having a negative sign and a enolized anion or a enol. Now show the shifting and show here this is a intramolecular aldol condensation. We get the corresponding closed ring structure here. Take down. Now finally, in the last step, it happens when the base abstract the hydrogen from the cyclic product so that elimination of hydroxyl occurs. As a result, we get the final chromon or coumarin. So the base will come and it will abstract the H plus ion so that OH minus will be eliminated out, so that the final product will be formed. See here, this is the base which abstract the H plus ion. See here, H, so that this bond is shifting here, O minus is coming here. So this happened reversible. See, the negative charge is shifting towards the oxygen. As a result, the double bond is shifting here and OH is eliminating out. Check again. See, a base is coming. Base will abstract the H plus ion and the bond will be shifting towards here. As a result, O minus will be formed. The pattern will be reversed. The minus ion shift the electrons to the carbon double bond. The carbon-carbon double bond shift the electrons towards this particular bond and OH minus is eliminated out, resulting the formation of final product. So we could say in Kostenecki reaction, a acid anhydride combined with a hydroxy aryl keton, a phenolic oxygen linkage is established, followed by cyclization, and final step elimination occurs. Take down. Listen carefully and take down. Show the arrow marks carefully. So the elimination occurs to have the final chromone or coumarin, which are derivatives of benzopyran and are isomers. Shall I give you examples to work out? Okay, I will give later. Now we move to another reaction, a ring formation reaction, that is Thorpe-Siegler reaction. Basically, Thorpe-Siegler reaction is a ring formation reaction or a cyclization reaction. But moving towards Thorpe-Siegler reaction, we have to see what is Thorpe reaction. A Thorpe reaction is a reaction between a nitrile. Nitrile means C triple bond N. C triple bond N or CN. If CN group is present in any organic compound, we term it as a nitrile or cyano group. So a nitrile and an alkoxide base. So we treat a cyanide and an alkoxide base. So they undergo certain reaction so that we get finally beta immunonitrile, from which we could have a alpha cyanoketone. So we get a alpha cyanoketone by treating a nitrile with a base followed by the reactions. So the reaction proceeds through the formation of beta immunonitrile. This is beta immunonitrile. This reaction is called Thorpe reaction. See here, I have a nitrile here treating with the base. So the base will abstract the H plus. So the first molecule, this is one molecule, attacks the second molecule to form a nitrile, immunonitrile, beta immunonitrile, which remove H plus or deprotonation occurs, followed by H plus, addition of H plus ion to form, see here, this is ketonic group, this is a C triple bond N. So this carbon atom is already here. This is a C double bond attached to this carbon atom. So this is a alpha position, we have CN group. So alpha cyanoketone. Basically this is a ketone and we have a cyanide group at the alpha position. This reaction is called Thorpe reaction. But when we carry out Thorpe reaction intramolecularly, it is called Thorpe-Siegler reaction, and taking place within the molecule, we get a cyclic compound. So Thorpe-Siegler reaction is a cyclic ring formation reaction. But Thorpe reaction is a reaction we get alpha cyanoketone. That is a intermolecular reaction. You got it? Now see here. Check down. Now see here. When a cyclization reaction occurs, it is called Siegler-Thorpe reaction. See here. I have a nitrile here. See the dinitriles, where are their positions? They are in the alpha and omega positions, or first and last position. I am using a base here. Take down, write down along with me. I am using a base here, NaOET, sodium ethoxide, so that a cyclic iminonitrile is formed, which on hydrolysis gives a cyclic cyanoketon. See here, a cycle has formed and there is a cyanide ring, CN ring at the alpha position. So we can say alpha cyanocyclic ketone. This reaction is called Thorpe-Sickler reaction. So very important, Thorpe-Sickler reaction is a intramolecular reaction of alpha omega dinitriles to form a cyclic cyanoketon. When it is a intermolecular reaction, the same product will be obtained, but it is not a cyclic compound. So if it is happening intramolecular within the same molecule, we get a cyclic cyanoketon, and that is Thorpe-Sickler reaction. Take down. So we have seen the difference between Thorpe reaction and Thorpe-Sickler reaction. So now we move to the mechanism. I will explain the mechanism step by step. You have to write it. Then you have to explain it with an example. I will only give the headings of the reaction steps. You have to write the compound and you have to explain it. Okay? See here. The mechanism is the base abstract a proton from the carbon atom carrying the cyanide group. See, this is the alpha omega dicyanide, okay, or dinitrile. This is the carbon atom carrying the CN group. That is, this carbon atom is attached to the CN group. So the base will come and take a hydrogen atom from here. We here have two hydrogen atom. So the base will come and take one of the hydrogen atom from here. Okay. So H plus is removed. As a result, we are getting a minus sign here. Are you sure? A minus sign here. That minus sign is stabilized by C triple bond N. Okay. So this is the first step. The base will abstract H plus from the carbon atom carrying the cyanide group. Now here we have a negative charge. Okay. Now take this cyanide group, this cyanide. C triple bond N. N is more electronegative than carbon. So naturally this carbon atom bears a positive charge, partial positive charge, and nitrogen bears a partial negative charge. So here we have a negative charge. This negative charge attacks this carbon atom. That means it undergoes cyclization with the carbon atom carrying the second cyanide group. Now the base abstracts proton from the imine group followed by protonation and hydrolysis give the final product. You got it? So in the first step, H plus will be abstracted from the carbon carrying cyanide group. Then intramolecular cyclization occurs, followed by protonation and hydrolysis will give you the final product. Take down. Okay, the mechanism step you have written. Shall I give the question? I hope you will write the mechanism. What is the first step of the mechanism? Tell me. See, the base abstract H plus from the carbon atom carrying CN group. Got it? So the base abstract H plus from the carbon atom carrying the CN group. See? So this carbon is having a negative charge now. Negative charge now. This negative charge attack the next CN group or nitrile group. I told you C triple bond N. So polarization could occur. So this negative charge of this carbon atom attached to the CN group attack here so that a ring is formed. A ring structure is formed here. See here, a ring structure is formed. Now the nitrogen is having a negative charge. So this nitrogen abstract H plus from the base. H plus from the base. Got it? Write down. Show the arrows clearly and take it down. I hope you have noted down in your book. See? So that we are getting NH. So this C triple bond N becomes C double bond NH. This nitrogen is having a lone pair of electron. This lone pair of electron attack H plus ion from the medium or H3O plus ion, hydronium ion. See here, this nitrogen is having a lone pair of electron. It attacks the H3O plus ion or hydronium ion so that this NH becomes NH2. So it is the lone pair of this nitrogen. So the nitrogen get a positive charge here. Now water molecule, hydrolysis happen, water molecule attacks this carbon atom. See here, the lone pair of oxygen, the lone pair of oxygen attacks this carbon atom so that shifting of electron pairs occur. So this bond is shifting towards here. As a result, nitrogen get positive charge here. This positive charge of nitrogen is removed. The positive charge of the nitrogen is removed now. so that I will get this molecule. Take down. Show the arrows. Take it very clearly. Hope you have finished. Okay. Now see here. What happens? NH2 will be eliminated by abstracting H plus ion. So NH3 will be eliminated. See the lone pair of nitrogen. Take hydrogen from the water molecule having a positive charge here. So NH3 will be eliminated out. And shifting of OH bond, resulting the formation of cyclic cyanoketon. See, cyclic cyanoketon. Take down. So check again. First step, base abstract the H from the carbon atom carrying the cyanide ring, followed by attack, intramolecular attack to form a cyclic compound. So the nitrogen atom or the present in the nitrile group abstracts H plus ion, followed by the elimination of NH3, resulting the formation of cyclic cyanoketon. This is the mechanism of Thorpe-Sickler cyclization reaction. So in Thorpe-Sickler reaction, alpha omega dinitriles undergoes cyclization reaction intramolecularly to form the final cyclic cyanoketon. Now we move to another reaction that is called azaloin condensation. Azaloin condensation. Alpha hydroxy ketones are generally called as azaloins. So, azaloins are the general name of alpha hydroxy ketones. And the preparation of alpha hydroxy ketones could be possible by using carboxylic acid esters. So this is a carboxylic acid ester which on reflexation using sodium, metallic sodium, in presence of aprotic solvents like benzene, ether, etc. This carboxylic acid ester undergo dimerization reaction to form alpha hydroxy ketones. That means two molecules of carboxylic acid esters in presence of sodium undergoes dimerization reaction to form alpha hydroxy ketone. See here, alpha position. This is ketone. This is the alpha position. So this is alpha hydroxy. This alpha hydroxy ketones are called azaloins. This is a common reaction. But the most important application of this reaction is that it could be used intramolecularly. That means if a molecule having two ester group, it reflects with sodium, undergoes intramolecular dimerization reaction to form cyclic alpha hydroxy ketones. See here, cyclic alpha hydroxy ketones. This is hydroxy group, this is the ketonic group. Alpha position, we have OH group. See, I am taking a diester. See, this is alpha omega diester. Alpha omega diester. Treating with sodium. So here dimerization occurs within the molecule, that is intramolecularly, to form alpha hydroxy ketones. This reaction is called Azaloin condensation reaction. Take down. So the mechanism occurs in 4 steps. 4-step mechanism occurs. So take down the steps. In the first step, the sodium will give electrons to the double bond of two esters, C double bond of ester molecule, to form ketyl free radical. We know ester is having C double bond O Me. So that ester is having a C double bond O group. To that particular C double bond O group, the sodium atom, which could easily donate electrons to the carbon atom to form ketyl free radicals. Take down. The first step is the formation of ketyl free radical. C double bond O. So polarization occurs. O minus will come. So that carbon is having a positive charge. To their electron from the sodium will be donated, so that the carbon carries a lone electron. Lone means a single electron. That is a free radical. Okay. Now in the second step, this free radical undergoes coupling reaction. See, if I take two molecules, the two free radicals has formed, and each free radical is having a lone electron in the carbon atom. So they combine together to form a coupled product or a dimerized product. If it is within the ring, they combine together to form the ring structure, and they eliminate the alkoxy group. See, ester is having a OMe group, so that will be eliminated out in the second step. Take down. In the third step, again the first step repeat. That means sodium Na will convert to Na plus and give the electrons to the double bonds of the keton to form sodium enodiolate. So a enol, sodium enolate is formed. a disodium enolate will be formed. And finally, water will come, neutralize this one, and the tautomerization will give you the alpha hydroxy ketone or acetylene. These are the 4 important steps of acetylene condensation. Take down. Now we have to use these steps and explain the mechanism. Noted it? See the first step. I have sodium here, Na plus. Sorry, Na, sodium. It converts to Na plus by losing 1 electron. And this single electron is donated to the ketonic carbon atom. See, this is the ketonic carbon atom. See here, a single electron is donating, single arrow, to this ketonic carbon atom. So a single electron is moving here, so a polarization occurs here, so that I will get a ketyl free radical here. See, a free radical or a lone electron is present in the carbon atom. So sodium ionization energy very low. It could be easily converted to Na plus ion, and that lone electron or electron donated by or given by the sodium atom attacks or reaches the carbon atom, resulting the formation of ketyl free radical. Take down the first step. So better you write this plus, write again this one. I show it as 2. You write this one big plus, again this one same one. That means 2 molecules of this ester give rise to 2 free radicals, 2 ketyl free radicals. Okay. Now what is the second step? These ketyl free radicals undergo dimerization. See here, they undergo this free radical and this free radical. They couple together, 1 electron from here, 1 electron from here. They couple together so that this carbon atom is connected with this carbon atom. These 2 carbon atoms are joined. So we will get carbon-carbon linkage. OMe, methyl group. This is OCH3 group, OCH3 group, that I am representing as OMe. This is the second OCH3 group and I am representing as OMe. Now we have O minus here. This shift to here, the minus charges will shift back, so that this OMe and this OMe will be removed to form a diketone. See, take down, carefully write down. See, show here only half arrow. Half arrow means only 1 electron is transferring, not a pair of electrons. So the second step is the formation of diketone. Now again sodium will act. Sodium will come and act. See here, again the sodium is coming. 2 sodium atom. The same thing repeats. So this carbon, it has this carbon atom and this carbon atom, they get free radicals. Neighboring carbon atoms become free radical. And they are joined together. See, this carbon electron, this carbon one electron. So they combine together to form a double bond here. And this is a double bond. And this is O minus, or enolate. Here it also a enolate. So we could say dienolate, sodium dienolate is formed. A double bond O minus is a enolate anion. Here is a sodium, here is a sodium. So we could say this is a dienolate. A dienolate is formed. Take down carefully, very careful and very easy. Now see in the final step what happens. This undergoes hydrolysis reaction with the water. So OH minus will come. See here, NaOH will be going. So OH is formed. This undergo tautomerization because enolates easily undergo keto-enol tautomerism. Keto-enol tautomerism. So that we are getting hydroxy ketone, alpha hydroxy ketone, which is called acetylene. You just imagine if this is a intramolecular, this ring is formed here. This is the mechanism of acetylene cyclization reaction. Take down